The agenda for today's webinar is discuss a little bit about what the InChI keys and InChI strings actually are and how they're being generated, and then how they're being implemented into the various STNext databases. We'll have a couple of search examples to show the value of including InChI keys in your search strategies, and we'll end today's presentations with a couple of considerations to help you create a quality search strategy. So what is InChI? Well, it is an international chemical identifier. That's what that actually stands for. And this was developed by IUPAC and the InChI Trust. They released this back in 2005. And this is based on the chemical structures. So they have created a unique identifier based on chemical structures. It doesn't have anything to do with names or molecular weights or formulas. It has all to do with these structures. And that's an important concept to remember. And this is a standardized, non-proprietary digital identifier. This InChI algorithm is open source. It's freely available, so anyone can have access to it. And obviously, we've incorporated that into various databases on STNext. Now, they started out with the InChI string, and that's what you see here. There are different layers, as they call them, for any compound that they will create an InChI string for. And it's broken into four different areas, four different levels of information, if you will. The first one is connectivity, and that's kind of the core structure, if you will. And then you have your isotope information, your stereochemistry information, and if you have any ions, any electricity sort of situations, you can see all of that information on the sample InChI string that you see below. You'll notice that it starts with InChI equals and then 1S. That is denoting the InChI version that was used in creating this. So once they actually have this structure, wherever they get the structure from, they can then generate this information about this structure in this alphanumeric way. Now, to you and me, that probably doesn't mean anything. We can't create an InChI string if we look at a structure. We just have to accept that the free-sourced algorithm software will generate the correct InChI string given a particular structure. Once you have your InChI string, then they can create what's called an InChI key. And the InChI key is significantly easier if you were ever to try to search this. If you go back and you look at the InChI string on the left-hand side, you notice that it has a lot of parentheses and dashes and commas and plus signs and forward slashes. So that would be pretty hard to duplicate as a search string. Well, if you look on the right-hand side at the InChI key, it's just a series of letters and a couple of dashes. Again, it's broken into those different areas that we talked about with the InChI string. But now you can see in the color-coded version on the right-hand side of the InChI key, again, those four categories or sub-layers, if you will. You have your main layer, your stereochemistry and isotopes, and then the version of the InChI key string. And then if it has any protons, any electricity sort of ideas. So now we've got a searchable term here in our InChI keys. We have taken this open source software and we have applied it to the structured searchable databases on the STNext platform that this would refer to. Obviously, this doesn't work with the Marcouche databases. It's all about specific structures. So you can see the three examples here of CAS Registry and the DCR database, the Derwent Chemistry Resource Database, and finally the Elsevier ReaxysFileSub database. In Registry, there's over 220 million substance records that do have corresponding InChI strings and InChI keys. With DCR, there's over 6 million substance records with that information as well. And for ReaxysFileSub, there are over 54 million records with that InChI information. You can see the one substance here and the 3 different identifiers given to each database producer, right? You've got a CAS registry number, then you've got a unique DCR number for the Derwent indexing system, and yet another unique identifier in the Elsevier accession number that you have in ReaxysFileSub. These are all the same substance, but they don't have anything in common in terms of the name here. 3 different indexing systems, 3 different numberings for this one substance. Well, now by adding the InChI string and InChI key information, you now have a common identifier across these 3 databases. That InKY field that you see at the bottom of this slide, this is going to be searchable, and this will be associated with this substance in all 3 of these databases. Unlike the CAS registry number or the DCR number, which only works in the Derwent database, or the Reaxys file accession number, again, only works with Reaxys files. So this is now an identifier across multiple databases. So here is an example out of Registry that has the information in terms of InChI strings, InChI keys. Again, have your structure first, and then your InChI string is generated, and then it's translated, if you will, into the InChI key. Again, the InChI key is the searchable version. Both of these fields are displayable, but only the InChI key is searchable. And that was a record out of CAS registry. Now, I've mentioned a couple times that there are different sub areas of the InChI key, one for the core structure, one for the stereochemistry and isotopes information, and one for any protonation, electricity, that sort of idea. So you've got these 3 different broken areas. You can, they're designated in the complete name by the hyphens. As you can see on the screen capture on the left-hand side of this slide, you can search at all 3 levels without truncation and get the relevant records. Now, why would you want to do that? So here's an example where we're looking at cysteine, and we've got 3 different possibilities here. We can search at the most specific level, right, which would have all the core structure, all the stereochemistry and isotope information, and if there's any protonation, anything like that. And when we search at that very specific level, we get 2 records of interest. If we do this again, but we take out the protonation concept, we now get an additional 9 records. Maybe these are salts, maybe they're different ions. And you can see an example here where we simply have the L-cysteine with the ion, or the carboxylic acid. And then finally, if you want to go even broader, you don't worry about the stereochemistry, the isotopes, or the protonation state of your substance when you want to do a search for it. You're just interested in this core structure. You can search at that level. And again, you can see you get additional hits that you would not have gotten with this additional levels of specificity. So you can plug into the system as broadly or as narrowly as you so desire. What is the value of having this additional information on these various databases in STNext? Well, this is very useful if you want to analyze information, if you want to sort your structures so that the similar structures are lumped together. You can do that by way of your InChI key information. You can also then be selective in your search if you're looking for certain stereoisomers, certain isotopes. Maybe the naming isn't always so consistent as we're going to see in one of the examples. And so maybe using the right part of the InChI key in your search strategy would help you with that as well. As I mentioned, you now have a substance identifier, or should I say a structure identifier that can be searched across multiple databases. So you can find identical substances across multiple databases much more easily than you could have before. You can also bring this information in if you're going outside of STNext. Let's say you start with an InChIKey out in the world, and then you want to bring it into STNext. You can do that as well now. You can now create structures for it, and you can search for this. As I mentioned, you can look for duplicate structures. That is something that we have not had before, that you could evaluate across databases, across registry to DCR, without doing a structure search, without doing a chemical name search. This is a way of saying this is the identical substance, and now let's see what kind of records they're indexing for this. So it also allows you to look for unique compounds, compounds you maybe didn't find in one of those other databases. As I mentioned, you can search the InChIKeys at 3 levels, the entire InChIKey, the first 2 parts, or the first part only. The InChI strings are not searchable. Okay. And again, this is that idea of searching at the various levels. This is run in CAS Registry. And when we have the core structure plus the stereochemistry and isotope information and the protonation site, obviously that's the most specific. That gives us L1, our smallest set. Then we take out the protonation ideas and that expands it to 11. And then when we finally look at just the core structure, we're all the way up to 92 substance records in registry. Let's go through a couple of examples here of the value of the InChIKey searching capability. All right, so here we are. In this case, we're in the Derwent chemistry resource database, and we're starting with a structure search. You can see for this particular structure search that we have a variable in R1, and that it can be 5 different atoms. It can be an oxygen, a sulfur, a hydrogen, a fluorine, or a chlorine. And when I run that structure search, in this case, a closed substructure search, I get 8 substance records out of the database. And then when I analyze that set for the InChIKey information, and you'll notice in this example that we're analyzing at a length of 14. You look at the search command, it's analyze set L2, going to search the field or analyze the field, the InChIKey, and we're telling the system to knock it off at 14 characters, as opposed to those 25 or 27 character options. That means all of our core structures will now be considered in the same part of my analysis. As you'll notice when I display the records for my analysis, the first 2 entries have 2 hits each. So there were 2 substance records in DCR that had the same core structure corresponding to this JUUB type InChIKey. And then there were 2 more records separate from what we had seen before, but they were related as well. They had the same core structure, maybe different stereochemistry, maybe different protonation, but the core structure was the same across these 2 DCR records. And then you can see one for each of the others. So just taking a look at the first one of these in my analyze command, again, there were 2 hits here, and they do look like the same record, except for the one on the left has deuteriums. Oh, okay. So there's the reason that the core structure is the same, but stereochemistry, isotopes, bingo. That's why it's got a different designation in that second portion of its complete InChIKey. These 2 are lumped together. Same thing with the second entry in my analysis that also had 2 hits. I wanted to see those 2 records. And again, you can see in this example, you have just the 1 oxygen, but the one on the left has 2 deuteriums as opposed to the one on the right. So same core structure, same InChIKey for the first, 14 characters. So nice feature there that able to pull together related substances in any one database. Now, new example. And again, this is a real world example. So this is where your searching acumen has to come into play here. You cannot just accept information blindly. You have to look at it critically, analyze it, and make sure that you are actually getting the information that you want to start with to use, go further in your searching. Here's an example to illustrate that. Looking for the stereo-specific version of penicillamine. Penicillamine, you can see that we're looking for the D stereoisomer. And then if we can, we want to limit that to records where it's being prepared. So that's all, at this point, all I have is the name for D-penicillamine. Am I right? And then I start in DCR, and you can see that there were no records in the database that had that chemical name. Again, you'll notice that I am searching with the search qualifier /CN. That is the chemical name. You can also think of that as standing for complete name. So in the DCR database, there is no substance record that has that specific name, D-penicillamine. Okay. Check registry. And there is one record in their database with that chemical name. Check the third of the structure searchable databases, ReaxysFileSub, and in that database, I get 7 hits. Okay, well, that's interesting. And so maybe I want to investigate the 7 records that I have now found in ReaxysFileSub. When I look at these records, the first, I think it's like 4 or so, all mixtures. So it was D-penicillamine and at least one other substance, as you see in these couple of records. If I go a little further down, then I do get to the point where I do see simple single compounds where one of the chemical names at least is the penicillamine that we have been looking for. So these all 3 might be of interest. And so you're looking, I've highlighted the 3 InChIKeys there with red boxes, but take another look at these records, and especially the one on the right. In addition to the name of penicillamine D, it also has the L version in the chemical name. But that one could be problematic. And if we look at the one on the left-hand side, even though it does mention D, I don't really see any stereochemistry in this one. The middle one does show some stereochemistry there. So take a look at these 3 records across the other databases and let's see what happens. So I started in DCR and I simply copied and pasted those 3 different InChIKeys. Now I've got 3 DCR records with the same InChIKey. Take a look at the records. You can see the first one that looks like it's flat, doesn't really show any stereochemistry at all. Something I might consider including in my Derwent searching because I'm always a little questionable about how much stereochemistry they include in their strategies. So maybe include that one. Look at the middle. Well, that's just L-penicillamine. Probably not one that we should be interested in. That seems to be the opposite of what we're looking for. We're looking for D. Look on the right-hand side, and we've got one where the name is simply penicillamine, but down in the Derwent DCR comment field, lo and behold, it says D isomer. So that's probably the one that we want to focus on in our strategy. But first pass here, let's just run all 3 and see what happens. I go in the WP index and I search that set, which is those 3 records. And I'm linking it to the Derwent roles of being produced or a product. That's the different role indicators that you see in this example on the left-hand side here of the screen capture, linking with the T operator, my DCR search L14, and I'm linking that to the roles are produced or being a product. I get 45 records out of the database, display the bibliographic information and the hit structure. And some of these look really good. I look at the title of this record here, and you can see it says synthesizing D-penicillamine. That's exactly the record that I'm looking for. So this is perfect. Strategy's working well. And I look at a couple more of these records, and these are preparing the L version. Not really what I want. And again, you can see here in the hit structures that it is talking about L-penicillamine. So because I did include that InChI key that I got from ReaxysFileSub, which they kind of said was D, but could be L, which DCR actually saw as L. Well, you probably should not have included in your strategy. As you can see, that's causing us to get false drops. What happens if I do that in Registry? Now I've got these three InChI keys once again. In this case, I get 4 hits. The reason I get a 4th hit is because one of the records listed this structure as a monomer and a polymer, polypeptide kind of idea. So there's our records for the other parts of this, and it's actually, let's see, I think it's the first one. Yes, the first record here is the polyamide form where it does include the monomer. So that's why this record is the 4th instead of 3. So, but you'll notice here, when we look at these, this looks like to be an L guy, L-penicillamine. I don't see any D's here. So we're going to run this but then we're going to see that it doesn't really work all that well. Here we have D-penicillamine. I see it there. And for this one, we have a DL. Okay, so I don't think this is really relevant either, but just to be on the safe side, in this case, we're going to run it with the CAS HCA plus role indicator of prep, right? You want to be prepared. And I got 302 records from that when I displayed bibliographic information plus hit structure. You can see that once again, I get some really good hits here. This first record here, green preparation of D-penicillamine. Perfect. What I want. Look at my hit structure. Yep, that's exactly the substance that I want. D-penicillamine, wonderful, good record. Looking at the second record, it also looks like that is exactly what we're looking for. That is the D version of that substance, and it is getting the preparation roles. Perfect, good hits. And we continue on, and guess what we're starting to find? We're starting to find records where we're getting the L version, not the D version. Again, if you look at the title up here on the one on the left, preparation of the L version. Okay, not right. So again, you want to be kind of critical when you get your information to make sure that it translates across the other databases in a way that captures records that really are of interest to you. And in this case, I just reran those searches with the one that is truly the D-penicillamine. I got 1 hit. When I put that into WP Index, I got my set of 30 compared to my original set of 45. And yes, all of the good ones were in there that we saw earlier, and the ones that I had the big red X in were not in this set. So they were not captured because I used the correct InChI key. Same thing in Registry. Again, when I use the one and only correct D-penicillamine InChI key. Got 2 hits because one of them is the polymer. So I'll go ahead, I'll use both of these. And I link that over to HCA Plus with the search role indicator of PREP for preparation or prepared. And I get 206 records there compared to 302. Once again, the good records that we originally saw are still in this set, and the ones that had the big red X that were showing up because of L-penicillamine are not part of this set. So again, just use these InChI keys, but use them knowledgeably. understand what they really are going for. Sometimes as you go across information centers or providers to other information providers, it may not translate as you expect. So just be aware of that. Okay. Our third and final example for today. This is where we're going to try to find unique substances. So we'll see what substances we capture on one database, and then go over to another database, eliminate those, and see if we've got any unique substance records in that database. And then we'll repeat that in our third database. Again, our three databases of interest: the CAS Registry database, the Derwent Chemistry Resource database, and the ReaxysFileSub database. In this example, I'm going to use this cyclic peptide as my structure example. And once I've drawn my structure, I'm going to do a full substructure search. That means that it's going to have that core structure, but it could basically have anything appended to it. There were no blocked sites in this particular structure. When I ran this first in Registry, I came back with 1,029 substance records. I then analyzed that set for the InChIKey. I used the complete InChIKey in this example. I did not limit it to just the core structure. And so you can see the results of this in the Registry database. Again, those ones with 2 hits is because of the record where it is listed as a monomer of a polymer. So you've got that core structure, but then you've got a monomer version of it as well. That's that second record. Do the same kind of structure search in DCR. Notice in this case, there were 141 structure substance records that were captured. Analyze the InChIKey for that set, and you can see the results for the first 10 in this screen capture. Again, the first 2, you got 2 hits, and again, that's because of the corresponding polymer type of entry in the database. Do this one more time for the ReaxysFileSub database, and when I do the structure search, full substructure search in the database, come back with 1,201 records. Analyze the InChIKeys there. You'll notice in some of these examples, you have 3 hits, you have 2 hits. That has more to do with Elsevier's indexing. Sometimes they have duplicate substance records in this database. So now we've run this across all 3 databases. Let's see if there's any unique records that we're getting across these 3 databases. So we'll start, we're in ReaxysFileSub. We're going to stay there, and we're going to pull only the unique records. So it's going to be search L6, which is my ReaxysFileSub set, not L3, which is the InChIKey analyzed set out of Registry. It's funny how you can do this. Usually you would have to be in multiple databases, but with InChIKeys, you can just pull them over in this way. L6, not L3, or L5. L5 is the corresponding DCR set where we had analyzed for all the InChIKeys. These, remember that L3 and L5 are the analyzed sets for InChIKeys. They're not the structure search sets. Did the structure search, and then we analyzed for the InChIKeys. That allows me to do this. Now, what I have are the substance records in ReaxysFileSub where there is not a corresponding substance record by way of InChIKey. I have to be careful how I say that, because when we get the considerations, I'll explain that in a little more detail. But this is a unique record. Didn't see a substance record like this in CAS Registry. Did not see a substance record exactly like this in DCR. Unique hit. We can do this across the other databases as well. So now we're in the DCR database, and we say, give me my DCR set where I don't have a matching InChIKey out of Registry, L3, or a matching InChI key out of ReaxysFileSub. That's my L7 set. And you'll notice that I did get 128 unique substance records out of DCR. Just displayed one of them, and you can see the structure with the highlighting in this screen capture. If you look at the bottom of this record, you can see the InChI string. Yikes, boy, it's a bit complicated, right? As you can imagine, this is a pretty complex structure. And then the InChI key itself is either your standard length there. Finally, we're looking at what is unique across registry. So we have our L2 set, and nodding out the analyzed InChI keys from DCR or your analyzed InChI keys out of ReaxysFileSub. That leads us to set L22 with 471 substance records. Just display the first record in that set. Again, you'll notice your hit highlighting on the right-hand side of your structure shown there. So each of these databases have unique substance records given a particular structure search. And we know that by comparing InChI keys, which are consistent across these three databases. Okay, now let's take a moment to consider what we've learned so far about InChI strings and InChI keys. First of all, they work well for the majority of substances in these three databases. There are some restrictions based on the InChI system as well. First being that it has a limitation as to how many atoms it can actually discuss in its system of InChI strings and InChI keys. Probably more important is the different indexing by the database producers. And we've been going through this since the beginning of CAS, where we say, you know, the great thing about the CAS platform, STN, whether it was STN Express, new STN, and now STNext, is that it had the wonderful CAS databases, and it had the wonderful Derwent databases, and it has the wonderful Elsevier databases all on one platform. And that is a great thing. But please remember that these three different database producers can look at the same information and come away with different indexing or different protocols for how they would index what they find in the same document that they're indexing. Just to give you the most common of examples, imagine that you have a pyridine ring. That's a C5N ring, and it's fully unsaturated. And you have a hydroxy group attached to it at position 2 compared to the nitrogen atom. Well, do you draw the double bond to the oxygen or to the nitrogen? Different database producers may deal with that tautomer differently. If it looks different in the database, then obviously it's going to get a different InChI string and therefore a different InChI key. And that has to do, again, with database producers' indexing systems, the way they deal with that. They may have indexing rules for this, that, and the other in terms of isomers, and they may not always be the same. CAS may not index something identically the way that Derwent does, and Derwent may not index it identically the way that Elsevier does. All three of these look at the world through different lenses. You have to take that into consideration whenever you are creating a search like this. So that's a very important tool. I mentioned the other limitation is that there is limitation inside the InChI system of 1,023 atoms. So it's not going to work for your really big compounds. It's not going to work for things like polymers or complex organometallics. Anything biological, that's got a variable structure, obviously that's just not going to work in this system. That's why when we showed the first couple slides of how many records were in CAS registry, in DCR, in ReaxysFileSub, it was a large percentage, but it was not 100% because there are some of those type of entries in each of those databases that do not. So InChIKeys worked really well for what I guess people in the industry would call small molecules, under 1,023 atoms. Large compounds, not so well. And obviously things like polymers doesn't work as well either. So to summarize, InChIKeys, unique substance identifiers. This is the first time we have anything like this, and it can be used across multiple databases. It's the first time you can get Registry and DCR and ReaxysFileSub to kind of talk to each other. So that's a great improvement across the STNext platform. And being added to Registry and DCR, I think it's been in ReaxysFileSub for a while now. We've added it to these databases for just that reason. But as with any good searcher, you always have to be a little bit critical in your strategies. You just can't grab something and automatically go, yep, this is what I need, as we saw with that example with the D-penicillamine. You certainly want to look at what it is you're using as your tool to go forward. So be a good searcher. Look at your information critically.